Space has no universal up or down, yet the planets give the solar system a useful floor, and spacecraft seldom leave it. Above that plane are the sun's poles, a different solar wind, and an outer boundary still being mapped. The answer is not a hidden roof or cellar, but familiar space, seen from a direction most missions cannot easily afford. While tonight, the room stays small, and those directions grow through verified science, measured missions, and calm uncertainty, all told at the pace of a nightlight. If nights like this are useful, a quiet subscription helps the next one find its way, while the rest may simply drift through the dark at its own unhurried speed, with no destination depending on wakefulness. Attention may loosen whenever it wishes. Nothing here depends on remembering what came before. The route begins with the word up, then follows the flattened inheritance of the planets. It passes Voyager's real family portrait, an old probe over the solar poles, a new view from Solar Orbiter, the unseen Oort cloud, and the tilted doorways of the Milky Way. Any stopping place is enough. A floor makes the word up feel obvious. Dropped keys fall toward it. Warm air lifts away from it. Even with closed eyes, the body keeps a quiet account of the pull below. Deep space supplies no such floor. Far from a planet, up is not a property of the universe. It is a direction chosen beside some local object. A spacecraft can point above a solar panel, north of an orbit, or away from the center of a world. Each phrase works because it names a reference. The solar system has a particularly useful reference. Astronomers call it the ecliptic plane. It is the plane of Earth's orbit around the Sun, extended outward like an immense, invisible sheet. The Sun sits near its center. Most planets travel close to it, so the sheet makes a natural map surface. The ecliptic isn't a wall. It has no edge, color, or physical skin. A probe crossing it would hear no tap. Nothing would change at the instant of passage. The line matters because clocks, star charts, and flight plans need a shared way to describe direction. An old globe offers a smaller example. Its equator is not a seam in the planet. The painted line simply helps one place relate to another. That ecliptic circle does much the same work, although it is drawn through empty space. When a mission team says a craft is above the ecliptic, the statement means the craft is on one designated side of Earth's orbital plane. Below means the other side. Those labels are conventions, not cosmic verdicts. Another civilization could reverse the names and change no physics at all. Solar north is a separate choice. The sun rotates around an axis, so its poles provide another frame. That axis leans roughly 7¼ degrees from a line perpendicular to the ecliptic. As Earth travels through the year, one solar pole and then the other tips a little more toward view. The small lean is enough to matter. A spacecraft may be north of Earth's orbital plane without hovering over the Sun's exact north pole. Engineers therefore state the frame carefully. Heliographic coordinates follow the Sun. Ecliptic coordinates follow Earth's orbital plane. Mission software can translate between those frames without moving the spacecraft. These systems can overlap on a single chart, rather like several transparent maps laid over one table. One map shows streets, another shows elevation, a third shows weather. None is the one true map, yet each answers a different question. The planetary orbits make the ecliptic feel more solid than it is. Venus, Mars, Jupiter, and the others circle in neighboring lanes. Their paths are not perfectly aligned. Together, the 8 major planets occupy a shallow fan. None tilts as much as 10 degrees from Earth's plane. Smaller objects roam farther. Even a few degrees grows into a large separation over distance. At the scale of Earth's orbit, 1 degree spans millions of miles from the reference plane. The planets still look remarkably orderly because the solar system itself is enormous. A slight angle has a long runway. Astronomers describe that separation with ecliptic latitude. An object in the plane has a latitude of 0. One ecliptic pole is positive 90 degrees, and the opposite pole is negative 90. The signs keep a calculation consistent, even though nature does not favor either side. Angle and height are not the same measurement. A craft 1 astronomical unit from the Sun at 30 degrees of latitude would stand half an astronomical unit from the plane. That height is about 75 million kilometers. A modest-looking slice of a circle becomes an enormous climb. Nothing pulls the craft back toward the ecliptic itself. The Sun's gravity pulls toward the Sun. In a properly inclined orbit, the machine passes above the plane, crosses it, continues below, and crosses again. Vacuum supplies no friction that would flatten the path. This is another place where the floor analogy must end. A bedroom floor supports weight and resists motion. The ecliptic supports nothing. It is closer to the middle line of a swimming pool, useful for judging position, but unable to push a swimmer toward it. Weightlessness does not remove local directions either. Astronauts aboard an orbiting station still use deck, ceiling, forward, and aft. The station and its crew are falling together, so loose objects do not settle. Named axes remain useful because the vehicle gives them a home. This practical habit extends to robotic missions. Star trackers determine attitude from patterns in the sky. Gyroscopes follow rotation. Sun sensors keep power arrays and shields oriented correctly. A coordinate frame turns those separate readings into one reliable pose. On a star chart, the ecliptic poles are simply the 2 points 90 degrees from the ecliptic circle. Nothing special shines there. Their importance comes from geometry, much as the center of a compass rose can matter on blank paper. Pluto makes the tidy picture untidier. Its orbit leans about 17 degrees to the ecliptic. Many comets arrive at steeper angles, and some circle backward compared with the planets. The shared floor is therefore a statistical habit. It is not a rule enforced on every object. This distinction settles the central question gently. What lies above and below the solar system is still part of the solar system. Near the Sun, those directions pass over its poles. Farther out, they cross streams of charged particles. dust, scattered comets, and the heliosphere. Eventually, the same path enters interstellar space. There is no ceiling overhead, nor is there an underside pressed against darkness. The familiar family of worlds becomes thinner in that direction, because most large bodies stay near their inherited plane. What changes is the density of things and the angle of view. From high above the ecliptic, the planets would trace nested loops around the sun. Their paths would resemble fine rings on dark velvet. From within the plane, those same orbits compress into a narrow band. Perspective turns a broad clock face into a thin line. Earthbound eyes live almost inside that line. The zodiac follows it across the night sky. Bright planets and the moon usually remain near the same celestial road. Their closeness is not a trick of the atmosphere. It is the distant appearance of a flattened system seen from within. A useful direction has now replaced an absolute one. Up means away from the ecliptic on one chosen side. Down means the opposite. Both lead through real regions with measurable particles, fields, and light. The words can rest lightly. They do not need to carry the whole universe. Like north on a bedside map, they only need to point the way. The planets inherited their narrow lane before any planet existed. About 4 6/10 billion years ago, the material that became the solar system was part of a cold cloud of gas and dust. Gravity drew a portion of that cloud inward. As it contracted, a faint original turn became faster. A skater offers the familiar version. Arms pulled inward make a slow spin quicken. A collapsing cloud follows the same conservation law, although its arms are filaments of gas, measured in vast distances. Rotation does not create gravity. It changes how the falling material arrives. Particles approach the young center from many directions. They collided, exchanged motion, and lost some of their wandering paths. Motion along the average spin survived. Vertical movement was more likely to be canceled by another encounter. The cloud gradually became a disk. It was thick, turbulent, and glowing near the center, not a polished record on a turntable. Gas churned through it. Dust grains met, stuck, broke apart, and met again. Within that busy layer, the early sun gathered almost all the system's mass. Today, the sun holds more than 99% of the solar system's known mass. The remaining fraction made every planet, moon, asteroid, comet, ring, and spacecraft. A crumb of the original inventory became a great deal of scenery. Inside the disk, grains assembled into pebbles. Pebbles became larger bodies. Collisions and gravity built planetary embryos, then worlds. The growing planets kept the disk's shared direction of travel. Viewed from above the sun's north side, all 8 major planets orbit counterclockwise. Their agreement is a fossil. No stone tablet ordered them to turn together. The common motion preserves the average spin of the cloud that formed them. A planetary system can therefore carry part of its birth into old age as geometry. The disk did not make every orbit identical. Large bodies tugged one another. Collisions changed speeds. gas pushed on young worlds, and some planets migrated from their first paths. The final system kept a thin overall shape while gaining wrinkles, tilts, and eccentric loops. While the gas remained, drag helped damp wild inclinations and eccentricities. A body moving through the disk met resistance, especially when it crossed the densest layer. Once the gas dispersed, that broad smoothing force disappeared. The surviving orbits could preserve their differences for billions of years. Meanwhile, the young sun drove material away. Radiation, hot plasma, and changing magnetic fields cleared much of the remaining gas and fine dust. What had been a thick nursery became a transparent system of separated worlds. Sunlight could finally cross the old disk without its dense birth cloud hiding every distant body. The old haze had finally thinned. Earth's orbit defines 0 degrees in the ecliptic frame. Jupiter's orbit is inclined by a little more than 1 degree. Venus leans by a little over 3. Mercury reaches roughly 7. These differences are small beside a right angle, yet they keep the planetary lane from becoming a perfect sheet. An inclined world crosses the ecliptic twice during each orbit. Astronomers call those crossing points nodes. One passage moves from the chosen southern side to the northern side. The other returns. Between them, the planet rises to its greatest angular distance from the plane, then settles back. The nodes are mathematical points. No gate waits there. Still, they matter for eclipses, encounters, and mission design. The Moon's orbit is tilted about 5 degrees to Earth's path around the Sun. Eclipses occur only when the Moon is near a node at the right phase. That modest tilt explains why every new moon does not cover the Sun. Most months, the Moon passes a little above or below it in the sky. A few degrees spare daylight from becoming a monthly ceremony. The asteroid belt also has thickness. Millions of rocky paths occupy a broad, busy volume between Mars and Jupiter. Many remain near the ecliptic, while others lean farther. A clean textbook ring is a useful first sketch, not a complete portrait. Beyond Neptune, smaller icy bodies preserve another flattened population. Some remain in a relatively cold, thin group. Others occupy a dynamically hotter, thicker cloud of paths. Here, hot describes orbital agitation, not temperature. The difference can be felt with an ordinary dinner plate. Imagine the main planetary orbits reduced until Neptune's path fits near the rim. Most major worlds would circle close to the plate's middle surface. Yet the smaller populations would not be paint on the china. They would form a shallow swarm above and below it. The real plate would be nearly 30 astronomical units in radius at Neptune. 1 astronomical unit is the average distance between Earth and the Sun. Light crosses that distance in a little over 8 minutes. The same light needs about 4 hours to reach Neptune. At that scale, thin does not mean small. The planetary realm is thin only compared with its width. A sheet of fog can still contain distances no aircraft could cross. Cosmic language often depends on such comparisons. The original disk also explains the Sun's equator, though not perfectly. Its rotation axis and the planetary reference plane retain a small mismatch. Researchers still study how early interactions produce that angle. a nearby young star, internal magnetic effects, or shifting material may have helped. Other stars confirm the general picture. Telescopes have photographed broad protoplanetary disks around newborn suns. Dark lanes and bright rings mark places where dust gathers or gaps appear. The solar system's ancient beginning is no longer imagined from its ruins alone. In the O-ring neb, Ulu, some young stars appear wrapped in small dark disks against glowing gas. Other observatories resolve rings around nearer stars in exquisite detail. A gap can hint at a growing planet, although other processes can shape rings too. The evidence shows that flattened nurseries are common, while every finished system keeps its own scars. Flattening does not end at one star. Many galaxies become disks because rotating matter settles toward a common plane. The mechanisms and scales differ, but a related principle returns. Collisions and gravity reduce random motion while preserving shared angular momentum. For the solar system, that history leaves a quiet visual result. Most worlds travel sideways from an earthbound point of view. Their orbits thread the same broad lane. The directions above and below stay comparatively open. Open does not mean vacant. It means the old cloud placed less of its heavy furniture there. Dust still glints. Comets still pass. The solar wind streams in every direction. That lane is simply where the largest rooms were built. Leaving the planetary lane is not forbidden. It is expensive in a very particular way. A spacecraft must change the direction of motion it already has, and that inherited motion is swift. Before launch, every machine on Earth circles the Sun with Earth. The average orbital speed is close to 30 kilometers each second. That is about 108,000 kilometers an hour, carried silently by oceans, buildings, launch pads, and sleeping cats alike. A rocket does not begin at rest on a cosmic map. It starts on a moving world. After escaping Earth's gravity, the craft still possesses much of Earth's sideways speed around the Sun. A mission sent toward Mars, Venus, or Jupiter reshapes that existing path. Most interplanetary journeys therefore stay near the ecliptic. Their targets already travel there. The craft can speed up, slow down, or adjust its angle by a modest amount. It joins a different solar orbit without throwing away the useful motion that Earth supplied. A polar journey asks for a larger turn. Imagine two arrows of equal length. One points along Earth's orbit. The other points straight over the Sun's pole. Moving from the first velocity to the second requires a new arrow that bridges their tips. For an ideal, sudden plane change, engineers use a compact relation. The required change in speed equals twice the current speed multiplied by the sine of half the turn angle. Its geometry is a triangle of velocities. It is simple on paper and stern in propellant. At Earth's distance, a craft in a circular solar orbit moves at roughly 30 kilometers each second. Turning that motion by 90 degrees in one instant would require about 42 kilometers each second of added change. The number is larger than the original speed because the old sideways vector must be replaced, not merely nudged upward. That figure is an idealized comparison. Real missions combine burns, gravity assists, and elliptical paths. They also begin inside Earth's own gravity well. The calculation is still useful because it reveals why a direct right-angle turn near Earth is unattractive. Altitude and inclination are different costs. A craft can travel very far from the Sun while remaining close to the ecliptic. Another can stay nearer while climbing to a steep solar latitude. Distance changes the size and energy of an orbit. Inclination changes its orientation. The distinction is easy to miss on a flat drawing. A long line toward Pluto looks more ambitious than a line rising off the page, yet the upward line may demand the harsher change in velocity. Paper hides the arrows that propulsion must bend. Plane changes become cheaper, where a craft moves more slowly. In an elongated orbit, the slowest passage occurs farthest from the Sun. A burn there can rotate the orbital plane for less propellant. The craft may then fall inward along its newly tilted track. Mission designers sometimes split a maneuver. One burn stretches the orbit outward. A second burn near the slow, distant end changes inclination. Later, another passage adjusts the size again. The route takes more time, but time can be lighter than fuel. Near the Sun, the opposite trade appears. A fast passage makes a pure plane change costly. Yet a burn there can alter orbital energy efficiently because the craft is already moving quickly. Engineers separate these effects and place each maneuver where its geometry helps. Nature can provide an even larger lever. A close planetary flyby redirects a spacecraft through gravity. The planet exchanges an immeasurably small portion of its own orbital momentum with the passing machine. No engine needs to supply the entire turn. Jupiter is especially persuasive. Its mass bends a flyby strongly, and its distant orbit gives mission designers room to reshape a path. The Ulysses spacecraft used Jupiter to leave the ecliptic and pass over the Sun's high latitudes. Its route first went outward so it could turn inward differently. Venus offers a gentler, repeatable tool. It is smaller than Jupiter, but close encounters can accumulate. Solar Orbiter uses a sequence of Venus flybys to raise its inclination step by step. The orbit tilts like a book, slowly lifted from a table. Gravity assists do not supply free energy in an absolute sense. The planet and craft exchange momentum. For the planet, that change is too tiny to notice, while the light spacecraft can gain or lose considerable speed relative to the Sun. Direction can change as well. Launch vehicles also exploit Earth's daily rotation. An eastward launch near the equator receives up to roughly half a kilometer each second from the spinning ground. Polar Earth satellites usually launch toward the north or south and receive less of that eastward gift. Safety and geography constrain those routes too. A solar polar mission faces a deeper version of the same geometry. Earth is already racing around the Sun in the ecliptic. A launch cannot simply point north and forget that sideways inheritance. The craft carries the old lane with it until thrust or gravity changes the vector. There is no air resistance to keep fighting once the turn is made. A properly inclined craft coasts along its new orbit. The costly part is establishing the path. Space remains generous after the ticket has been paid. The amount of propellant grows rapidly because rockets must lift fuel that helps lift more fuel. This is the rocket equation's quiet severity. Extra change in velocity is not added like another cup of water. Each increment can demand a much larger starting mass. Electric propulsion can build substantial changes over long periods with very little thrust. Solar sails can alter orbits using light. Proposed missions have combined close solar passes, sails, and planetary assists to reach high latitudes faster. None removes the underlying geometry. An ion engine may push with a force comparable to the weight of a few coins. It can keep pushing for months, using propellant efficiently. A solar sail needs no propellant for the light pressure itself, though its acceleration is also small. Patient thrust can draw curves that a short chemical burn cannot afford. Navigation must then manage years of accumulated effects. A tiny pointing error, a planetary misdistance, or pressure from sunlight changes the final orbit. Radio ranging and star measurements keep the long turn on course. The phrase "barely explored now" has a mechanical meaning. No guard protects the region above the plane. It is reached by a turn that ordinary mission budgets rarely justify. Space agencies usually spend scarce energy where planets, moons, and immediate science targets already wait. The unexplored direction is therefore an artifact of motion. Humanity lives on a fast carousel and launches from its rim. Traveling outward follows the spin. A route over the top means changing the music of the ride. The mathematics can settle into one small image. Earth carries every departing craft sideways at 30 kilometers each second. To go high above the planetary lane, that long invisible arrow must bend. The darkness offers no resistance. Only the turn costs fuel. One spacecraft has already looked inward from well above the ecliptic. The result is famous, although its viewing angle is often forgotten. Voyager One's family portrait came from roughly 32 degrees above the planetary plane. Launched in 1977, Voyager One flew past Jupiter in 1979 and Saturn in 1980. After the Saturn encounter, gravity sent the craft north of the ecliptic on a path that would not return to another planet. The main camera work seemed finished. Nearly a decade later, astronomer Carl Sagan and others continued urging the mission to look home once more. The idea carried scientific value and a rare kind of perspective. Controllers eventually prepared a final sequence. On February 14, 1990, Voyager turned its cameras back toward the Sun. The craft was about 6 billion kilometers away, close to 4 billion miles. Radio instructions had taken hours to reach it. The machine then swept its gaze across the inner darkness. Next came a portrait requiring 60 frames. Some used the wide-angle camera to map the setting. Others used the narrow-angle camera to find individual worlds. The whole sequence was more mosaic than snapshot, assembled from separate glances. 6 planets appeared: Venus, Earth, Jupiter, Saturn, Uranus, and Neptune left small traces in the images. Mercury was too close to the sun's glare. Mars was lost in scattered light. Pluto was too faint and small for the attempt. Earth occupied less than a single pixel. A ray of sunlight scattered inside the camera, and happened to pass through its position. The little world seemed suspended in a pale beam, although the beam was an optical artifact, yet the dot itself was real. That frame became the pale blue dot. Its power came from scale rather than detail. No continents appeared. Weather could not be seen. A planet holding every human life at the time had become a fraction of light against a dark field. The broader family portrait is less often shown. It places the captured planets in their directions around the distant sun. Because Voyager was elevated above the ecliptic, the view contains genuine vertical perspective. It is not an edge-on picture taken from within the ordinary lane. Still, it is not the clean overhead diagram sometimes imagined. 32 degrees is a high balcony, not a point directly above the solar pole. The planets remain separated across a huge sky. Each is a dot, and several are missing. No camera could expose the bright sun and faint planets as one natural-looking scene. Different frames required different settings and filters. The familiar assembled portrait, therefore, combines careful observations rather than reproducing what a human eye would see in one glance. Electronic camera tubes served in place of modern solid-state sensors. Each frame contained 800 lines by 800 samples. Filters separated portions of visible light, and ground processing assembled selected exposures into color. Pointing had to be cautious, because direct sunlight could damage the cameras. The sequence began with views farther from the sun and ended nearer the center. Engineers balanced one last portrait against the safety of a spacecraft already headed into darkness. At 32 degrees, Voyager's height above the plane was substantial, but its distance from the sun was greater still. The geometry opened the planetary arrangement without placing the craft over the pole. A mapmaker would call the view oblique. This corrects two opposite myths. Humanity has photographed the planetary family from above its usual plane, yet no one has photographed the entire solar system as a luminous clockwork model from a true polar distance. Both statements can sit comfortably together. The distinction matters because honest curiosity is stronger than a manufactured absence. More remarkably, one aging probe looked from a slanted height across billions of kilometers, using cameras designed in the early 1970s. Voyager transmitted the data slowly. Its signal reached Earth as a faint radio whisper. The image files arrived over subsequent months, while the spacecraft continued outward. Those last frames were stored and handled by systems with less capacity than an ordinary modern pocket device. After the portrait, the cameras were turned off. They would have found no nearby targets, and the mission needed power for fields and particles instruments. The optical eyes ended their work after looking back at the place that built them. Scientific work did not stop. Instruments continued sampling the solar wind, magnetic fields, cosmic rays, and the boundary toward interstellar space. A camera had made the philosophical picture. Other sensors pursued the physical one. From Voyager's position, the plane of the planets had begun to open. The separation was earned indirectly during the Saturn flyby. A close pass by Titan shaped the encounter and sent the craft on its northward trajectory. Planetary gravity again became a hinge. The image also shows why a distant portrait is difficult. Moving far enough away makes the whole system more compact in angle, but the planets grow dim. Rising higher improves the geometry, but costs trajectory energy. The sun remains overwhelmingly bright at the center. Meanwhile, the planets were moving during the sequence. A family portrait is never a fixed arrangement, only one set of positions at a chosen time. Light from each world left at a slightly different moment before meeting Voyager's lens. Back on Earth, the mosaic required calibration and interpretation. Dust spots, scattered rays, and weak targets had to be distinguished. The small blue point survived that scrutiny, exactly where orbital calculations said Earth should be. An ideal top-down portrait would demand a camera able to manage all three problems. It would need a high inclination, great distance, and enormous dynamic range. Even then, most objects would be unresolved points. The elegant rings would exist mainly as calculated paths, not visible tracks. Orbits do not glow on their own. The fine loops in textbooks are lines of prediction. A real polar photograph would show a bright sun and scattered specks against blackness. Time-lapse measurements could reveal the clockwork, slowly. Voyager's mosaic is quieter than the imagined poster. Its emptiness is part of its accuracy. 6 tiny worlds occupy 60 separate frames. Between them lies almost all the picture. The portrait's elevated angle offers a truthful first look above the lane. It does not solve every wish for perspective. Instead, it does something more human. Home becomes a point, then remains intact. The old frames remain a bridge between geometry and feeling. 32 degrees is only a number until the blue speck appears. Then, above the solar system, becomes a place from which Earth can nearly vanish, while still reflecting enough sunlight to be found. Ulysses crossed the high solar latitudes with no camera at all. Its view of the poles arrived as streams of numbers, each one describing particles or fields passing an instrument. The machine learned the shape of an invisible weather system by feeling it move. ESA and NASA built the mission as a partnership. Space Shuttle Discovery carried Ulysses into orbit in October of 1990. Rocket stages then sent the probe away from Earth on one of the fastest departures attempted at the time. Its first destination was not the Sun. A direct turn into a steep solar orbit would have demanded too much propellant. Ulysses traveled outward to Jupiter, reaching the giant planet in February of 1992. Jupiter bent the trajectory downward from the ecliptic. In the chosen coordinate system, the craft passed south of the planetary plane and began a long orbit around the Sun. The new path tilted about 80 degrees to the Sun's equator, only 10 degrees short of a perfect polar orbit. That detour resembled walking away from a tall wall to find a staircase around its side. Jupiter stood far from the desired science target, yet its gravity made the essential turn. The largest planet served as a silent piece of mission hardware. Ulysses needed more than 6 years to complete one solar orbit. It ranged from near Earth's distance to beyond Jupiter's. During high-latitude passes, It remained more than twice as far from the Sun as Earth is. The probe went over the poles in angle, not close over the solar surface. A first southern polar passage began in 1994. In September, Ulysses reached a latitude just above 80 degrees south, at about 2 3/10 astronomical units from the Sun. Light took roughly 19 minutes to cross that distance. A polar pass lasted for months rather than one dramatic instant. Mission scientists often defined the high latitude interval as everything beyond 70 degrees. The spacecraft sampled a long arc, allowing changes with time to be separated from changes with latitude. After crossing the southern region, Ulysses swept through lower latitudes near the Sun and climbed north. The pair of passages completed the first direct survey from one solar pole to the other. Later orbits repeated the route under different magnetic conditions. The Sun would have appeared smaller there than it does from Earth. It still governed the surrounding plasma. Charged particles flowed past the craft, carrying traces of solar magnetism into the dark. Near a quiet phase of the solar cycle, Ulysses found fast solar wind streaming from broad polar regions. Speeds reached about 750 kilometers each second. Such a flow could cross the Earth to Moon gap in less than 9 minutes. Slower and more variable wind occupied lower solar latitudes. The contrast produced a broad structure that Earthbound spacecraft could not sample directly. Ulysses moved through latitude, as another probe might move through layers of atmosphere. Solar wind is not air. It is a thin plasma of electrons and atomic nuclei, chiefly protons. Near Earth, only a few particles may occupy each cubic centimeter. Their great speed lets the sparse flow carry energy and magnetic fields across the solar system. Ulysses measured those fields as well. The Sun's rotation winds the outward magnetic pattern into a spiral. At high latitude, the geometry becomes different from the wavy current sheet near the solar equator. The polar route gave the first sustained measurements there. During solar maximum, that quiet pattern did not remain fixed. The magnetic field became more complex, and the clean bands of fast polar wind changed. Ulysses observed the Sun through more than one stage of its roughly 11-year activity cycle. That longevity mattered. One pass can mistake weather for climate. Repeated passages allowed researchers to compare different solar conditions. The probe completed high-latitude surveys around the mid-1990s, the early 2000s, and again late in that decade. Its instrument suite also counted energetic particles and cosmic rays. The solar wind helps shield the inner system from some charged particles arriving from the galaxy. As solar activity changes, the filtering changes too. Ulysses watched that relationship from latitudes other missions rarely occupied. Dust struck a detector aboard the craft. Some grains belonged to the solar system. Others arrived from interstellar space, passing through the heliosphere on the surrounding galactic flow. Tiny impacts turned invisible grains into measurable electrical signals. The dust detector measured the charge released when a grain struck at high speed. From that brief pulse, Researchers estimated impact speed and mass. Microscopic grains still produced signatures the instrument could distinguish. Ulysses also detected bursts of dust associated with Jupiter. The grains were extremely small and electrically charged, so the planet's rotating magnetic field helped fling them outward. A giant world was shedding a fine, invisible trail. Radio instruments listened for bursts from the Sun and Jupiter. Plasma sensors sampled local conditions. Each device occupied a modest part of the spacecraft, yet together they described an environment wider than any camera frame. The lack of a camera was deliberate. Ulysses was designed in the 1970s for in-place measurements. A photograph would have shown the Sun as a bright disk from far away. The essential science lived in particles that could not be seen. For stability, the spacecraft spun about 5 times each minute. Its long antenna pointed toward Earth, while instruments observed around it. Data traveled home at low rates through the deep space network. An unhurried thread stretched across hundreds of millions of kilometers. Power came from the decay heat of plutonium. The source weakened gradually, and onboard heaters competed with instruments for energy. Engineers found careful ways to keep fuel from freezing and systems from cooling too far. By 2009, declining power made continued operation impractical. The mission ended after more than 18 years. Ulysses remained in its solar orbit, dark and silent, still inclined steeply to the planetary plane. The final difficulty was partly thermal. Hydrazine fuel in narrow lines had to remain warm enough for attitude control. As electrical power declined, heaters consumed a growing share. Controllers tested careful operating patterns, but the energy margin continued to close. No landing marked the end. There was no atmosphere to burn the craft. Commands stopped. The radio fell quiet, and the machine continued along the curve Jupiter had given it. Its legacy is a map made from touch. The solar poles were not empty caps. They were sources of fast wind, regions of organized magnetism, and gates through which galactic particles entered differently. The high direction had weather. Ulysses also changed what exploration could mean. A place need not be photographed to be visited scientifically. For years, a small spinning probe crossed an unseen stream above the Sun and translated each passing particle into a patient signal home. In March of 2025, the Sun's south pole entered a camera's view for the first time. The image did not come from directly overhead. Solar Orbiter needed only a modest tilt to see beyond the bright rim that hides the pole from Earth. The European Space Agency and NASA operate Solar Orbiter together. It launched in February of 2020. The spacecraft carries instruments that taste the local solar wind and telescopes that study the Sun from a distance. 10 instruments share the mission. 4 make measurements around the spacecraft. 6 observe the Sun and its atmosphere remotely. Coordinated campaigns connect a patch on the star with particles that later cross the orbit. Its orbit repeatedly approaches inside Mercury's path. At the closest planned passages, the craft comes within roughly 42 million kilometers of the Sun. Sunlight there is more than 10 times as intense as it is near Earth. A heat shield faces that glare. Small doors open for several telescopes, like dark peepholes cut into a protective wall. The shield's outer surface can withstand temperatures near 500 degrees Celsius, while the instruments remain sheltered behind it. Heat alone does not reveal a pole. The spacecraft also needs latitude. Repeated encounters with Venus gradually tip its orbit away from the ecliptic. Each flyby makes a measured adjustment that no onboard fuel tank could easily provide by itself. By that March, Solar Orbiter viewed the Sun from about 17 degrees below its equator. That angle sounds slight beside a right angle. It was enough to expose the southern polar region as a surface rather than a narrow edge. The first campaign combined observations from several days. A camera that measures visible light and magnetic polarization recorded the surface. Other instruments studied ultraviolet light and the motion of solar material. The views were released in June of that year. Next, the campaign built a combined polar view rather than treating one exposure as complete. Separate measurements were corrected and joined. The final product was therefore both an image and a measured map. Velocity maps used small shifts in the color of spectral lines. Material moving toward the spacecraft shifted one way, and material moving away shifted the other. Those changes exposed circulation that a still brightness image could not show. The pole did not appear as a permanent white cap. It looked granular and restless, covered by the same boiling texture seen elsewhere on the Sun. Convection cells carried hot plasma upward and cooler plasma down, making a field of bright centers and darker borders. The surface also rotates at different rates by latitude. Regions near the equator turn faster than regions closer to the poles. This differential rotation helps twist magnetic fields and complicates any attempt to follow one feature for long. Magnetic measurements added another layer. Patches of opposite magnetic polarity lay close together around the pole. Solar Orbiter arrived near a busy part of the solar cycle, when the Sun's global magnetic field was reversing. The reversal happens around solar maximum. Mixed regions appear as the old polar field weakens, and a new dominant polarity eventually settles. A compass taken there would not find a simple, steady north or south. This magnetic renewal is connected to the solar dynamo. Flowing, electrically conducting plasma inside the Sun stretches and reorganizes magnetic fields. The process drives the roughly 11-year sunspot cycle, though many details remain under study. Polar observations are valuable because magnetic flux gathers and changes there. Measurements from near the ecliptic see the poles at a severe angle. Features become compressed, and the line of sight magnetic signal becomes harder to interpret. Earth receives a small seasonal advantage from the Sun's known axial lean. During part of the year, the South Pole tips slightly toward Earth. 6 months later, the North Pole receives the better view. 7 degrees still leaves most polar detail near the limb. Solar Orbiter's larger angle opened a clearer window. It was like moving from the front row of a theater toward a side balcony, finally seeing part of the stage that scenery had concealed. The spacecraft was not the first to travel over the sun's high latitudes. Ulysses measured the polar environment decades earlier from much farther away. Solar Orbiter added direct imaging and remote magnetic maps from closer range. That difference joins two kinds of truth. A local detector can feel one stream with great precision. Remote telescopes can see patterns spread across a surface. Together, they connect the source region to the material flowing outward. The mission's remote cameras observe eruptions, magnetic loops, and the fine structure of the atmosphere. Its local instruments later encounter particles and fields that may have left those regions. Matching the two is like recognizing a river downstream after watching rain fall on a distant slope. Solar Orbiter also watches the sun rotate. At close approaches, its orbital motion briefly helps it keep pace with parts of the solar surface. Features remain in view longer than they would from Earth, allowing their changes to be followed with less interruption. The polar angle will increase through later Venus encounters. Its mission is designed to gain better views rather than leap into a perfect 90-degree orbit. Each added degree improves the map and refines measurements that were once extrapolated from the edge. Venus encounters must be timed with care. A small error would alter both the next solar pass and the following planetary meeting. Years of geometry are folded into a few hours near the cloud-covered planet. No single image settles the poles forever. Solar magnetism evolves. The solar cycle advances. Instruments have limits, and models must connect observations across depth and time. The first view is a beginning made valuable by repetition. That picture also softens a common expectation. A solar pole is not a lonely summit. There is no peak, ice, or fixed marker. It is a chosen region on a rotating sphere of plasma, identified by an axis that cannot be seen directly. At the surface, hot gas rises and falls with a texture like countless grains. Above it, magnetic arches guide glowing material. Farther out, some field lines open into space and help shape the solar wind. Solar Orbiter turns the title's direction into a place of origin. Above the planetary lane lies not merely a different view of the sun, but access to the regions that organize its changing field. The pole is both geography and machinery. History came gently at this scale. A 17-degree tilt, accumulated through quiet meetings with Venus, was enough. The sun did not need to be conquered from overhead. It only needed to be seen from slightly beyond the old line. The sun's outer atmosphere does not end at a neat surface. Some of its plasma becomes hot enough to escape gravity and expand into space. The resulting solar wind passes over the poles, through the planetary plane, and far beyond Neptune. Near the visible surface, gravity holds matter tightly. Higher in the corona, temperatures reach more than 1,000,000 degrees. Collisions become sparse. Magnetic fields guide the flow, and part of the plasma gains an outward route. The wind consists mainly of protons and electrons, with smaller amounts of helium and heavier ions. It is electrically balanced overall, yet its moving charges carry the sun's magnetic field. Empty space acquires a faint, changeable grain. The Sun loses roughly 1 million tons of material each second through this flow. Although that number sounds immense, it is extremely small compared with the Sun's total mass. The star can continue at a similar broad rate for billions of years. At Earth's distance, solar wind pressure is measured in billionths of a pascal. A hand would never feel it. Large magnetic fields and wide solar sails can respond because they collect the effect across area and time. At Earth's orbit, the flow often travels between roughly 300 and 800 kilometers each second. The fastest parcels could circle Earth in under a minute if they followed the surface. Their actual path is outward through a near vacuum. Fast streams commonly emerge from coronal holes. These are regions where the magnetic field opens into space instead of looping back nearby. They look darker in extreme ultraviolet images because the local plasma is thinner and cooler than surrounding coronal material. A coronal hole is not an opening in the Sun. The visible surface remains beneath it. Its name marks a darker region in the hot atmosphere where plasma has an easier magnetic route outward. Ions carry chemical clues. Ratios of elements and electrical charge states reflect conditions near the source. Researchers can compare a passing stream with remote solar images and infer which kind of region released it. During a quiet solar minimum, large coronal holes often occupy the polar regions. Broad, fast streams then pour from high latitudes. Closer to the solar equator, slower wind is more irregular and can arise near the borders of magnetic structures. The pattern changes near solar maximum. Polar holes shrink or reorganize. Active regions multiply, and the magnetic map becomes tangled. Fast and slow flows then meet in more complicated arrangements throughout the inner system. The Sun rotates beneath its escaping wind. Near the equator, a rotation takes about 25 days. From Earth's moving viewpoint, the apparent period is closer to 27 days. The turning source winds magnetic field lines into a spiral. Imagine water from a rotating lawn sprinkler. Each droplet travels outward, while successive droplets leave from changing directions. The result curves across the lawn. Solar plasma behaves differently in detail, but the rotating source picture captures the broad geometry. The magnetic sectors have opposite polarities. Between them lies a thin boundary called the heliospheric current sheet. The sheet is electrical in the plasma sense, not a solid membrane. It ripples outward from the Sun across billions of kilometers. Because the Sun's magnetic axis does not align perfectly with its rotation, the sheet becomes wavy. Textbooks often compare it to a ballerina's skirt. The image is graceful, though the real structure has folds, dents, and changing layers. Earth crosses the ripples as it orbits. Instruments may record the magnetic field pointing generally toward the Sun, then generally away. Nothing visible passes the windows. A compass in the solar wind simply finds the large field changing sign. High above the ecliptic, the crossings can become less frequent during quiet solar conditions. That helped older polar measurements reveal a more ordered field. Near maximum, the distinction softens as the whole magnetic arrangement becomes complex. Packets of fast wind can catch slower material ahead. The flows compress one another and form broad, rotating interaction regions. As the sun turns, these structures sweep past planets repeatedly, like spiral weather bands without clouds. The journey to Earth takes time. A fast stream may cover one astronomical unit in a little over 2 days. Slower flow can need 4 days or more. The sunlight announcing a change arrives in 8 minutes, long before the material itself. Meanwhile, the flow expands as it travels. A parcel that began dense becomes increasingly dilute, while collisions become rare. Particles keep a memory of earlier temperatures because their charge states can freeze once encounters are too infrequent to change them. That delay lets solar observatories compare cause and arrival. A dark coronal hole turns into position. Days later, detectors near Earth sample the stream associated with it. The connection is reconstructed through timing, composition, speed, and magnetic direction. Some solar eruptions launch denser magnetic clouds. They are separate from the steady wind, though both travel through the same medium. When one reaches Earth's magnetic field, it can help produce auroras and disturb technology. The effects are monitored, then they pass. Above the sun, the wind is not calmer merely because fewer planets travel there. It carries its own architecture. Open field lines, fast streams, and magnetic polarity give the high latitudes a changing texture. Parker Solar Probe approaches the source from a different direction. Its orbit stays near the planetary plane, but dives close to the sun. In late 2024, it passed within about 6 million kilometers of the visible surface, closer than any earlier spacecraft. Images released in 2025 showed the wind near its origin with unprecedented proximity. A camera observed faint structures moving through the corona and captured eruptions interacting with the current sheet. The view linked broad, remote images to local measurements deeper in the flow. Parker does not need a polar orbit to complement polar science. It changes radial distance instead of latitude. One mission samples the wind close to its source. Another changes the angle. Together, different directions separate effects that otherwise overlap. The sun fills the solar system with more than light. Every second, plasma leaves in all directions. Most of it never touches a solid object. It passes through enormous volumes, carrying a magnetic memory of where it began. Far from the sun, the wind thins and slows against surrounding interstellar matter. Close by, its separate streams can still be traced to regions on a turning star. The high road over the poles is part of that continuous motion. No breeze would brush a face there. The density is far too low, and the particles are far too energetic. Yet an instrument can feel the stream as clearly as a curtain feels an open window, one tiny impact after another. The solar wind builds a vast enclosure around the planets. It is called the heliosphere, a region dominated by plasma and magnetic influence flowing from the sun. Its outer form is real, but its full shape remains difficult to see. The surrounding galaxy is not empty. Meanwhile, the sun moves through a thin mixture of gas, dust, cosmic rays, and magnetic fields. Solar material presses outward, while this local interstellar medium presses back. Their meeting creates a boundary on an immense scale. Closer to the sun, the solar wind moves faster than waves can travel through its own plasma. Farther out, pressure from the galactic environment forces it to slow and heat. Beyond that broad, disturbed region lies the Leo pause, where solar wind plasma yields to interstellar plasma. The name suggests a clean skin. In practice, the boundary is dynamic. Magnetic fields drape, particles cross by complex routes, and the boundary shifts with the solar cycle. A surface drawn on a diagram is an average through restless material. Voyager One entered this frontier after decades of travel. In 2012, its instruments recorded the transition into interstellar plasma. Voyager 2 made a separate crossing in 2018. Their paths sampled 2 points, both on the forward side of the heliosphere. The crossings occurred at distances near 120 times the distance from Earth to the Sun. Light needs roughly 17 hours to travel that far. Voyager needed more than 30 years. At that radius, a sphere would have a circumference of more than 100 billion kilometers. The HEEE sphere is unlikely to be a sphere, but the comparison conveys the reach of a boundary built by a thin wind. Both paths crossed at slightly different distances. Conditions changed with time and direction. That difference is useful evidence, but 2 needle holes cannot reveal the whole shape of a dark tent. Early illustrations often gave the heliosphere a comet-like tail. The moving sun formed a rounded nose, while material stretched downstream behind it. This picture was reasonable and remains one possibility at large scales. Other models produce a shorter, rounder form with 2 broad lobes. The sun's magnetic field may channel solar material into structures that resemble a deflated crescent or a soft croissant. A familiar bakery comparison is memorable, though no pastry captures the evolving plasma. Researchers do not yet agree on one simple outline. Results depend on interstellar magnetic fields, neutral atoms, solar activity, and how particle populations are modeled. The honest portrait is a family of tested shapes, constrained by incomplete views. Mapping from inside requires a special messenger. A fast-charged particle near the boundary can steal an electron from a neutral atom. Once neutral, it is no longer guided strongly by magnetic fields. It can travel in a straighter line back toward the inner solar system. A detector records the arriving atom's direction and energy. Many such arrivals build a remote map, rather as raindrops on windows around a house might reveal a storm beyond the walls. No single atom carries a picture. The pattern appears through patient counting. An earlier mission found a surprising ribbon of enhanced arrivals across the sky. The feature is linked to the surrounding magnetic field and the outer interaction region. Its precise explanation has inspired several models rather than one final answer. The ribbon does not glow as a visible band. It emerges from a sky map after many detections are sorted by direction and energy. A bright pixel may represent months of atoms arriving one by one. Now a newer observatory continues that work. The Interstellar Mapping and Acceleration Probe, known as IMAP, launched in September of 2025. It carries 10 instruments designed to study the heliosphere's boundary and the particles moving through it. IMAP traveled to a gravitational balance region about 1.5 million kilometers sunward of Earth. From there, the spacecraft can keep a steady relationship with Earth and the Sun while scanning the sky. A broad sun shield protects its measurements from direct glare. The observatory spins as it works. Its instruments sweep great circles, while Earth's annual motion changes the viewing geometry. Over time, those circles build nearly complete maps of incoming particles. The mission reached its observing region in January of 2026. Primary science operations began in February. By then, all 10 instruments had returned first observations, showing that the full suite was working in space. Some instruments map neutral messengers over different energy ranges. Others measure solar wind ions, energetic particles, interstellar dust, and magnetic fields. Together, they connect local samples with the distant boundary that produced many of the incoming signals. The maps will change over time. Solar wind launched today can take about a year to reach the outer heliosphere. A neutral atom created there may need another year to return. An image assembled near Earth can therefore contain a delayed history of the Sun. Neutral interstellar atoms also enter from outside. Some lose electrons or become ionized near the Sun, joining the charged population carried by magnetic fields. Their abundance and direction provide another sample of the galactic material around the heliosphere. That time lag gives the boundary a slow rhythm. The solar cycle swells and relaxes the heliosphere, but the response is not immediate. Effects travel outward, interact, and send information back. The full conversation takes years. Directions above and below the ecliptic are essential to this mapping. The heliosphere is three-dimensional, and the interstellar magnetic field does not politely align with the planetary plane. High-latitude signals help distinguish a long tail from broad lobes or a more rounded shell. The enclosure should not be confused with the whole solar system. Distant comets remain gravitationally tied to the Sun, far beyond the heliopause. The solar wind's domain ends much sooner than the Sun's gravitational family. Nor does crossing the heliopause mean leaving every solar influence. Gravity has no sharp wall there. Sunlight continues, weakened by distance. The phrase interstellar space refers to the surrounding plasma environment, not freedom from the Sun in every sense. From Earth, the heliosphere cannot be photographed from outside. Humanity lives inside the structure being measured. Models combine the Voyager crossings, sky maps, local particle data, and the known interstellar flow. The resulting uncertainty is not a blank. A boundary exists. Its approximate scale is measured. Particles arrive. What remains unsettled is the global contour and the way that contour changes. The direction above the sun therefore opens onto a scientific room still being furnished. Instruments at one quiet point near Earth count atoms that have crossed a boundary billions of kilometers away. 2 old Voyagers touch that frontier directly. Between them lies a shape no eye can see at once. It breathes over years, pushed from within by a star and molded from outside by the galaxy. The best map is still arriving, one neutral particle at a time. Far beyond the solar wind's boundary, gravity may hold a vast population of frozen bodies. Astronomers call this inferred reservoir the Oort cloud. No telescope has taken a direct picture of one of its members resting at home. The cloud is known through visitors. Long-period comets arrive from immense distances on narrow, stretched orbits. When their paths are calculated backward, many point toward a remote source surrounding the solar system in all directions. Dutch astronomer Jan Oort developed the modern version of this idea in 1950. He noticed that long-period comets did not seem to be arriving fresh from interstellar space each time. Their orbital energies suggested a distant storehouse, still weakly bound to the sun. The word cloud can mislead. It is not a mist, and its objects do not crowd together. Each icy body may be separated from its neighbors by distances larger than planetary systems. The name describes a distribution, not something with visible vapor. Estimates place its inner regions at a few thousand astronomical units from the sun. The outer edge may reach tens of thousands, perhaps around 100,000 astronomical units. Uncertainty remains large because the source itself has not been seen. At 100,000 astronomical units, sunlight needs roughly 1 year and 7 months to arrive. That distance is about 1 6/10 light years. It reaches a substantial part of the way toward the nearest star system without coming close to touching it. The sun's gravity is extremely weak there. It can still hold a slow-moving object, but passing stars and the Milky Way's broad tidal pull can alter the orbit. A small nudge, accumulated over ages, may send a body inward or release it entirely. The cloud probably began closer to the young planets. Icy leftovers encountered Jupiter, Saturn, Uranus, and Neptune. The giant planets scattered many outward. Some escaped the sun, while others entered distant orbits that stellar and galactic perturbations gradually rounded into many orientations. This history explains the contrast in shape. The planets formed in a disk. Over time, the remote comet reservoir became more nearly spherical after countless weak nudges. Above and below the ecliptic, its population may be as important as the population around the sides. The total number is unknown. Models allow hundreds of billions of objects larger than small mountain fragments, perhaps more. Their combined mass is even harder to estimate. Assumptions about sizes and early planetary scattering change the answer. Darkness makes direct detection severe. A small body thousands of astronomical units away receives almost no sunlight. The light it reflects fades on the outward journey, then fades again while returning to a telescope. Distance dims it twice. Heat offers little help. Temperatures are only a few degrees above absolute zero. A dormant nucleus releases almost no gas. It lacks the bright coma and tail that make a comet noticeable near the sun. The reservoir is therefore observed when one member falls inward. As sunlight warms its ices, gas escapes and carries dust. A dim, ancient body acquires an atmosphere wider than a planet, announcing a home that remains invisible. The journey can take millions of years. A comet near the outer cloud may spend most of its orbit moving with extraordinary slowness around the distant turn. It then accelerates during the long fall toward the sun. Kepler's laws stretch time with distance. Neptune circles once in about 165 years. A body tens of thousands of astronomical units away can need millions of years for one circuit. One orbit can outlast whole species. Voyager One will not soon provide a close inspection. At its current outward speed, the probe may need roughly 3 centuries to reach the cloud's inner neighborhood. Crossing the broader region could take tens of thousands of years. Even then, a chance passage near an object would be unlikely. The cloud's volume is enormous. Sending a craft through it is not like sailing into a field of snowballs. It is more like crossing a dark ocean whose scattered islands cannot be seen from shore. The boundaries are not crisp. Some models divide the reservoir into an inner, somewhat flattened region and an outer, more spherical one. Other terms describe overlapping populations. The available comet orbits constrain the possibilities without drawing a firm border. A few observed objects remain far beyond Neptune and never approach the giant planet closely. Their detached orbits may preserve hints of an inner reservoir, past stellar encounters, or an unseen history of planetary scattering. None is a directly observed member of the distant classical cloud. Sedna is one such body. Its closest point lies around 76 astronomical units from the Sun, while its farthest point reaches many hundreds. Even there, it remains much closer than the broad distances usually assigned to the Oort cloud. That gap shows the observational problem. Telescopes can find a modest world hundreds of astronomical units away if it is large enough and happens to be near its closer passage. The same object at tens of thousands would fade far beyond present surveys. Nearby stars may occasionally stir the outer objects. The effect depends on a star's mass, speed, and passing distance. Most encounters are remote. Over billions of years, even gentle flybys can rearrange a weakly held edge. The Sun itself was probably born in a cluster, where other young stars were once nearer. Early encounters may have trimmed, stirred, or exchanged some distant material before the stellar siblings dispersed through the galaxy. The Milky Way provides a constant tide as well. Galactic gravity pulls on both the Sun and a distant comet, but not by precisely the same amount. That slight difference can rotate an orbit until its inner end begins falling toward the planetary region. An inward path does not point straight at the Sun. It is a long ellipse with angular momentum preserved. The comet may pass through the planetary zone, brighten, and return outward. A close planet or solar pass can reshape the next orbit. Because evidence arrives through these altered survivors, reconstruction is delicate. Astronomers calculate original orbits before major planetary encounters where possible. They distinguish a truly new arrival from a returning comet whose path was changed last time. The Oort cloud remains one of the largest structures commonly given the solar system's name. It lies far beyond every planet and beyond the heliosphere. Yet it may consist of the same early material once tossed from the young planetary disk. Above the Sun, the imagined path eventually enters that sparse sphere. There is no bright threshold. One more dark body may pass somewhere across a volume measured in light years, still taking a few million years to complete its quiet fall. The absence of a photograph does not leave an empty claim. Comet trajectories, planetary scattering, and galactic perturbations fit together into a testable explanation. The cloud is inferred with care, and its edges remain honestly soft. Comets reveal how loosely the solar system obeys its planetary floor. Some travel close to the ecliptic, others descend from steep angles. A few circle the Sun opposite the direction taken by every major planet. An orbital tilt is measured against a chosen plane. 0 degrees follows the common planetary direction in the ecliptic. 90 degrees is polar. An angle greater than 90 means the object is retrograde, moving around the Sun the other way. Halley's Comet offers a familiar example. Its orbit is inclined about 162 degrees. That is equivalent to being only about 18 degrees from the ecliptic, while traveling backward around it. The geometry feels surprising because drawings often show a steep diagonal. Important here is the reverse direction. Near an ecliptic crossing, Halley meets the planetary traffic more like a train on the opposite track than a carriage in the same procession. Halley returns roughly every 76 years, though planetary tugs alter the interval. It last passed near the Sun in 1986. Its next expected return to perihelion is in 2061. At closest approach to the Sun, Halley moves at about 54 kilometers each second. Far from the Sun, it slows dramatically. The changing speed is the same orbital exchange seen in every ellipse, carried to a striking extreme. Halley's solid nucleus is only about 15 kilometers long and 8 kilometers wide. It is irregular, dark, and rich in ices mixed with dust. The surface reflects only a small fraction of incoming light, darker than fresh asphalt. Near the Sun, warming ice changes directly into gas. Escaping jets lift dust and form a broad coma around the nucleus. Sunlight and the solar wind then draw material into tails that can extend for millions of kilometers. The nucleus turns as uneven jets fire from its surface. That rotation changes which areas receive sunlight and can make brightness pulse over hours or days. A comet is an active little world, not a uniform snowball. Some ices lie beneath a dark, insulating crust. Fresh cracks expose volatile material, while other vents fade. Images of visited nuclei show pits, cliffs, smooth deposits, and boulders under a sky too thin to scatter blue light. A tail does not simply trail behind the direction of travel. The ion tail points generally away from the sun under the influence of the solar wind and magnetic field. Dust forms a gentler curve because its grains retain more of the comet's orbital motion. An outbound comet can therefore appear to move with a tail ahead of it. The sun, not the route, sets the main direction. Another common picture becomes more accurate with one small turn. Halley's present orbit is short compared with those of the most distant comets. It may have originated in the remote Oort reservoir before planetary encounters altered its period. Today, it returns on a schedule that human records can recognize. Chinese, Babylonian, and European observers described earlier appearances. The English astronomer Edmund Halley later connected several records as returns of the same object and predicted another passage. Success gave the comet his name. Dust released on repeated passages spreads along the orbit. When Earth crosses parts of that trail, grains enter the atmosphere and make annual meteor showers. The comet may be far away, while its old particles draw brief lines of light. Most long-period comets take more than 200 years to orbit. Their inclinations are spread broadly across the sky. Some arrive prograde, some retrograde, and many approach far from the planetary plane. That wide distribution supports a roughly spherical source. A thin, distant disk would send visitors mainly through a narrow band. Instead, the inner solar system receives them from high northern and southern latitudes as well. Short-period comets often tell a different story. Many are linked to the flattened populations beyond Neptune. The KYE per belt extends outward from roughly 30 astronomical units and contains icy objects on a range of tilted paths. This belt is thicker than the major planetary lane. It is still fundamentally disk-like. Nearby scattered populations reach higher inclinations and more elongated orbits, creating a gradual transition rather than one tidy edge. Encounters with Neptune can push some icy bodies inward. Later encounters with the other giant planets shorten or reshape their paths. Jupiter has such a strong influence that a large family of short-period comets carries its dynamical signature. The two reservoirs produce different patterns without labeling every comet perfectly. A relatively flat outer region supplies many frequent returners. Meanwhile, a remote spherical region supplies many long-period arrivals. Individual histories can be complicated. Comets also change each time they warm. Jets spin a nucleus or alter its orbit slightly. Surface layers crack, collapse, and lose volatile ice. Some objects fade into dormancy. Others break into fragments under heat and internal stress. A dormant object can resemble an asteroid until weak activity appears. The boundary between categories is therefore partly behavioral. Composition, origin, and present appearance do not always fit one simple label. Their activity occupies a tiny fraction of each life. Almost the entire circuit can pass in cold invisibility, followed by a few bright months near the sun. The glowing tail is a brief weather event around an ancient dark stone. Still, the solid object remains small even when its coma becomes enormous. A nucleus the size of a town can surround itself with a cloud wider than Earth. Thin gas and dust catch sunlight across a large volume, making the visitor look grander than its solid core. Crossing the ecliptic adds no special flash. A comet can pass from above to below without noticing the human reference plane. What matters physically is its distance from the Sun, its velocity, and the fields and particles it encounters. The plane still helps astronomers follow the route. Nodes mark the crossings. Inclination describes the tilt. Perihelion marks the closest solar passage. With a few elements, an orbit can be reconstructed as a curve through three-dimensional space. Those numbers predict where a faint body should reappear. Telescopes return to the calculated patch of sky. A point moves against the stars. Each new position refines a path that may extend beyond any direct view. Above and below the planetary lane, comets provide the moving landmarks. They do not fill the darkness. Instead, they cross it, briefly carrying evidence from regions that cameras cannot yet inspect. The solar system's floor was never a locked arrangement. It was the main current in a much wider sea. Halley glides against that current, dark for most of its circuit, then unfolds two pale tails when sunlight reaches its ice. The word north changes when the map changes. Earth has a north pole, the Sun has another. An ecliptic pole points perpendicular to its plane, and the Milky Way has a separate pole above its galactic disk. These axes do not line up. A spacecraft climbing north of the planets would not be traveling straight above the Milky Way. The planetary plane is tilted by about 60 degrees to the galactic plane. Two dinner plates can hold the picture. Set one plate flat for the Milky Way's disk. Tilt a second by roughly 2/3 of a right angle. The smaller plate represents the ecliptic, with the Sun near its center. Still, the analogy distorts every scale. Solar north points diagonally through the galaxy. Galactic north rises perpendicular to the Milky Way's broad stellar disk. Neither direction owns the word in an absolute sense. Earth adds a third tilt. Its rotation axis leans about 23½ degrees from the perpendicular to its orbit. That lean produces the seasons and defines the celestial poles used on the night sky. The celestial equator is Earth's equator, projected among the stars. It crosses the ecliptic at 2 points. The Sun appears to pass those crossings at the equinoxes, when day and night are nearly equal in length. Polaris currently sits close to Earth's north celestial pole. It seems almost fixed while other northern stars circle around it. The star does not mark ecliptic north or galactic north, and it will not remain Earth's guide forever. Earth's spin axis slowly precesses like a top. One full sweep takes about 26,000 years. The north celestial pole therefore traces a circle among the stars, selecting different pole stars across deep human time. By contrast, the ecliptic pole is steadier on that scale because it follows Earth's orbital plane rather than the spin axis. Planetary perturbations change the orbit slowly, so it is not eternal either. Astronomical coordinates are precise conventions built on moving nature. Galactic coordinates use the Milky Way itself. The galactic equator follows the middle of its disk, as seen from the Sun. Its poles point toward thinner lines of sight through the disk, away from the bright Milky Band. That band is the combined light of distant stars and glowing material seen edge-on from within. Its mottled dark lanes are dust clouds blocking background starlight. Looking toward a galactic pole leaves much of the crowded disk to the side. The North Galactic Pole lies in the direction of the constellation KOH, Bear-Uk NYECs. South points toward Sculptor. These names are sky addresses from Earth, not labels carried by the galaxy itself. The ecliptic and galactic equators cross at two opposite regions of the sky. One crossing lies near the rich constellations around the galactic center. The other lies toward the winter stars on the far side. Their intersection makes the zodiac and Milky Way appear to weave through one another. Near those crossings, a telescope can face both zodiac dust and crowded galactic foregrounds. 90 degrees farther along either great circle, one kind of foreground may ease, while the other remains. The tilted maps have practical consequences for observing. If an observer stood on a planet around another star, the same galactic poles would describe the disk. The constellations would change. Near and distant stars would rearrange, and Earth's familiar pictures would dissolve. The solar system also travels around the galactic center. One orbit takes roughly 230 million years. Since the planets formed, the Sun has completed only about 20 such circuits. During that journey, the Sun bobs relative to the galaxy's midplane and encounters changing neighborhoods. The detailed motion is measured from stars and gas around it. Galactic up and down become directions within a much larger orbit. Even the Milky Way's disk is not a rigid flat plate. It has thickness, a central bulge, a bar, spiral features, and a warped outer region. Young gas and stars occupy a thinner layer than older stellar populations. The plane is an average through structure. Coordinate systems keep this complexity manageable. A catalog can give an object's longitude and latitude in the galactic frame. Another can use right ascension and declination tied to Earth's sky. Software translates between them, without claiming one is more real. A fourth frame belongs to the local horizon. Altitude measures height above the horizon, while azimuth turns around it. As Earth rotates, a star's altitude changes through the night, even though its catalog coordinates remain almost fixed. This everyday sky frame truly has an up. Gravity defines the horizon through the observer's local vertical. Two observers far apart on Earth have different verticals, each pointing away from the planet's center. The word north is conventional in another sense. Once an axis is chosen, one end receives the northern label, so maps share a handed orientation. Reversing both labels would alter charts and signs, but the orbits would continue unchanged. Mission navigation depends on the same discipline. A direction stated without a frame can produce serious confusion. Engineers attach axes to a spacecraft, a planet, the sun, or a star field. Every attitude command says which map it means. An ordinary room does this unnoticed. A shelf has a top. Books have a front. People have left and right. Rotate the book, and its own top moves while the room's ceiling remains where it was. Space removes the shared ceiling, so the labels must travel with their objects. Solar north belongs to the sun. Ecliptic north belongs to an orbital plane. Galactic north belongs to a disk of hundreds of billions of stars. The title's upward direction is therefore only the first rung of a scale ladder. Above the planets leads over the sun's poles. Continue far enough, and that line cuts diagonally through the Milky Way rather than leaving through its pole. A true journey above the galaxy would require a different heading. It would also demand distances beyond present spacecraft. The Milky Way's stellar disk is about 100,000 light-years wide, and its surrounding populations extend farther. No confusion needs to remain between the frames. The angles can coexist like transparent compass roses. Each one makes a local pattern easier to describe, while the stars continue moving without labels. At night, the evidence crosses overhead. The zodiac traces the planetary plane. Across it, the Milky Way marks the galactic one. Their paths meet at steep angles, two pale roads drawn by two different kinds of flattening. The roads shift with season and hour. In 1 month, the Milky Way arches high after dusk. Another month leaves the same part below the horizon. The planes remain tilted in space while Earth's nighttime side turns beneath them. Still, the sky carries more than one north, because nature has made more than one disk. A young cloud flattened around the sun. Galaxies flatten on a grander scale. Their poles point into separate stretches of the same patient dark. Some directions are prized not for what fills them, but for what stays out of the way. Astronomers seek dark windows with fewer foreground stars, less galactic dust, and weaker sunlight scattered by material in the solar system. The faint glow along the ecliptic is called zodiacal light. Dust grains between the planets scatter sunlight toward Earth. Under a dark sky, the glow can appear as a soft cone after evening twilight or before dawn. The grains are tiny and widely separated. Together, they make a flattened cloud centered broadly on the planetary plane. Looking near the ecliptic peers through more of that dust. A view toward its poles usually reduces the foreground. The galactic plane creates a different veil. Stars crowd the view, while dust absorbs and reddens visible light. Wisps of cool material also emit at infrared wavelengths. A clean field for a distant galaxy survey must avoid both bright stars and complex dust. The best window may therefore need two maps. It should sit far enough from the Milky Way's band and in a region of low zodiacal background. Nearby bright objects that could scatter light inside a telescope must also be avoided. Euclid uses that careful selection. The European Space Observatory launched in 2023 and works near a stable region beyond Earth. Its wide survey is designed to map enormous numbers of galaxies and trace how cosmic structure changed with time. The observing region lies roughly 1.5 million kilometers beyond Earth, opposite the Sun. A sun shield can keep the bright Sun, Earth, and Moon on the same side of the spacecraft. The telescope then faces a broad, cold sky. Euclid's primary mirror is about 1 2/10 meters across. One instrument records visible shapes at high resolution. Another spreads near-infrared light into colors and spectra, helping estimate galaxy distances. 3 deep fields receive repeated observations. Their locations were selected for unusually low foreground contamination and long visibility. One lies in the northern sky, while 2 lie in the south. Together, they offer clear keyholes into the distant universe. The fields also support calibration. Repeated images reveal whether the instrument response changes and let surveys overlap with observations from other telescopes. A scientifically quiet sky becomes an engineering reference as well. Repeated visits add faint detail. Light from very distant galaxies arrives 1 photon at a time against detector noise and foreground glow. Returning to the same field builds exposure, reveals change, and improves the map. Euclid measures galaxy shapes for signs of weak gravitational lensing. Foreground matter bends light from more distant galaxies by tiny amounts. Statistical patterns in millions of shapes help chart matter that does not shine. It also studies how galaxies cluster across distance. The combined information tests the expansion history of the universe and the growth of structure. A quiet patch of sky becomes a laboratory for questions larger than the field itself. Hubble demonstrated the power of such patience earlier. In 1998, the Space Telescope stared at a small southern field chosen to complement its original northern deep view. The Hubble Deep Field South accumulated exposures across several wavelengths. That patch covered only a few arc-minutes of sky. It was far smaller than the full moon. Within that apparent pinprick, long exposures revealed thousands of remote galaxies at different stages of cosmic history. If the full moon were a large coin, the field would occupy a tiny mark on its face. That small angle still opens a cone through the universe. Nearby space contributes little volume, while distant layers contain more and more galaxies. No nearby landmark made the field special. Its value came from being comparatively ordinary and clear. The telescope looked where foregrounds were quiet enough to let the background speak. Deep fields are not empty before observation. They contain faint stars, thin cirrus, detector artifacts, and galaxies too dim for short exposures. Choosing the region reduces confusion. Data processing then separates remaining foreground light from the distant signal. Cosmic rays strike detectors and leave bright marks. Small changes in pointing move real stars and galaxies in predictable ways, while detector blemishes stay attached to pixels. Multiple exposures allow the two to be separated. The telescope never gathers an untouched view. Every final image is built through calibration, alignment, background subtraction, and checks against independent data. The darkness becomes useful because its imperfections can be measured. Solar dust is one of those foregrounds. The Zodiac cloud likely receives material from comets and asteroid collisions. Grains spiral slowly toward the sun under subtle radiation effects, while new collisions replenish the population. Spacecraft traveling outward have measured the glow fading. Pioneer observations beyond the inner system showed that Zodiac light weakens greatly past the main dust cloud. Physical distance can provide a darker sky than direction alone. Juno's instruments found another trace by accident. During its cruise toward Jupiter, small dust impacts knocked microscopic pieces from the spacecraft's solar arrays. Cameras recorded the resulting bright streaks, allowing researchers to infer where impacts were most common. The discovery showed how an observatory can become a dust detector without carrying a dedicated dust instrument. A grain too small to see produced a measurable spray. The background revealed itself through a tiny knock on hardware. Dust is troublesome for deep imaging and valuable for solar system science. Its distribution records collisions, comet activity, and the forces moving small grains. A foreground removed from one study becomes the subject of another. Galactic dust has the same double life. It obscures distant galaxies in visible light. In infrared and radio observations, the dust reveals cold clouds where stars may form. Clean and cluttered depend on the question being asked. Directions above and below the main planes can reduce both kinds of clutter, but never erase them. The galaxy has a halo. High inclination dust occupies the solar system. Light also scatters inside instruments, and the universe supplies diffuse backgrounds of its own. The phrase dark window is therefore relative. It means a line of sight with a manageable foreground, not a hole in creation. Every black field gains structure when enough light is gathered. An observatory at a quiet balance point turns slowly, shielding itself from the sun. A chosen field remains clear of Earth and Moon. Detectors cool, guide stars hold steady, and remote galaxies add their faint counts. The scene contains no dramatic crossing. Science grows through repetition. One exposure joins another, until a tiny part of the sky becomes deep enough to carry billions of years. Above the bright zodiac and away from the Milky Way's crowded lane, the darkness is useful. It is not more empty. Instead, it is less interrupted by nearby light, like a clean window after the lamps in a room have gone low. Beyond the Milky Way's bright disk, the galaxy continues through a sparse halo. Stars become much rarer above and below the plane. Yet an enormous structure surrounds the familiar spiral. It holds old stars, compact clusters, torn streams, and unseen mass inferred through gravity. The Milky Way's luminous disk spans roughly 100,000 light-years. Gas, dust, and many young stars remain concentrated near its middle layer. The Sun sits about 26,000 light-years from the center, inside that broad, rotating structure. Around it, the disk has thickness. Older stars wander farther above and below than newly formed ones. Their vertical motions create overlapping thin and thick populations, rather than a hard upper surface. Beyond them, the stellar halo is diffuse and roughly rounded. Its stars can occupy elongated, tilted, or even backward galactic orbits. The orderly rotation of the disk gives way to a quieter swarm with many directions. Many halo stars are ancient and contain relatively small amounts of elements heavier than helium. They formed before generations of stars had enriched the galaxy with carbon, iron, and other products of stellar interiors. Their chemistry acts like a worn maker's mark. Astronomers measure patterns of elements in starlight and compare them with motion. Groups that share both can preserve evidence of a common origin, even after spreading far apart. Globular clusters stand out as compact islands. A single cluster may hold hundreds of thousands of old stars in a sphere only a few hundred light-years across, or less. From inside, its sky would be crowded with brilliant neighboring suns. Their distribution gave an early clue that the Sun is not near the galactic center. Clusters gather around a point in the direction of Sagittarius, far from Earth's position. Dust hid much of that inner galaxy in visible light, but the surrounding cluster system outlined the deeper arrangement. These clusters orbit the Milky Way on paths that pass above and below the disk. Some may have formed with the galaxy. Others may have arrived inside smaller galaxies, later absorbed by the Milky Way. Gravity stretches those smaller systems. Stars are removed along their orbits and form narrow streams. A stream can wrap around much of the sky while remaining hard to notice against foreground stars. The European Gaia Observatory transformed this search. From 2014 through early 2025, it repeatedly measured positions, brightness, colors, and motions for about 2 billion stars. Its observations ended, but years of analysis and future data releases remain. Tiny shifts across the sky reveal how stars travel. Distance estimates and radial velocities add further dimensions for large samples. The result is not a photograph of the galaxy from outside. It is a moving map assembled from within. In that map, streams appear as stars sharing a path. Some trace disrupted clusters. Others are remnants of dwarf galaxies consumed long ago. Their coherent motion can survive after their original shape has vanished. Researchers have identified overlapping debris from several ancient mergers. The Milky Way grew by collecting smaller systems, as well as forming stars in its own gas. Its halo is partly an archive of those quiet collisions. Collision sounds violent at human scale, but galaxies are mostly empty space. Stars from two merging systems almost never strike one another directly. Gravity changes their routes over hundreds of millions of years, while gas clouds can compress and form new stars. The stellar halo may extend around 300,000 light-years across, depending on how it is defined. Its outer edge is difficult to mark because member stars become rare, and neighboring satellite galaxies overlap the same space. Small companion galaxies move through the halo as well. The largest are visible from southern skies as soft clouds. Dozens of fainter satellites have been found through surveys that identify slight overdensities of old stars. Their orbits help estimate the Milky Way's total mass. A more massive galaxy can hold faster or more distant companions. The calculation remains uncertain because only a short part of each immense orbit has been observed. Gravity reaches farther. Motions in the Milky Way, the paths of satellite galaxies, and gravitational lensing all indicate a much larger halo of dark matter. Some illustrations place its broad scale near 1,000,000 light-years across. Dark matter should not be pictured as black fog blocking starlight. It appears transparent and interacts weakly with ordinary matter, apart from gravity and current evidence. A photon can cross the halo without meeting an opaque wall. The invisible component outweighs the galaxy's stars and gas. It supplies much of the gravity that keeps outer stars and satellites bound. Its particles, if they are particles, have not yet been identified directly. That number is model dependent. Dark matter has not been photographed as a cloud. It is inferred because visible matter alone cannot produce the observed gravitational behavior. The halo's shape and outer boundary remain active research questions. Stellar streams help test it. A stream follows the galaxy's gravitational field, so gaps, bends, and speeds can reveal the underlying mass distribution. The faint ribbon becomes a probe stretched across thousands of light years. One cluster can lose stars from both sides. Leading stars move slightly ahead in the orbit, while trailing stars fall behind. Over time, the compact cluster draws two delicate tails around the galaxy. The tails are cold in a dynamical sense. Their stars have similar motions, so a small disturbance can remain visible. Such precision makes a stream sensitive to both known structures and possible clumps of unseen mass. Passing lumps of matter may disturb a stream. The disk and central bar also create effects. Researchers compare detailed models, careful not to assign every irregularity to one invisible cause. Above the galactic plane, a traveler would first see the Milky Way's spiral structure open beneath it. That journey remains imaginary. Even at the speed of the fastest probes, rising a few thousand light-years would take far longer than recorded human history. Light makes the distance plain. A signal needs 1 year to cross a light year. It would need tens of thousands of years to reach a truly external vantage, where the galaxy's broad spiral became easy to see. No spacecraft is required to study the vertical structure. Star motions provide depth. Radio telescopes map gas. Infrared light passes through dust. Gamma rays reveal energetic particles. Each messenger supplies a different transparent layer. The halo is dim because its material is spread widely, not because it is unimportant. It contains evidence of the galaxy's youth and mass. Its old stars remember systems that no longer exist as separate galaxies. One scale has folded into another. The planetary plane became the solar poles. Next, the solar direction met a tilted galactic disk. Above that disk, structure continues through ancient clusters and nearly invisible streams. There is no final blank immediately beyond the Milky Way's bright lane. The galaxy softens outward. Star by star, its visible population thins into a halo whose gravity reaches farther than its light. The space above a galactic disk also contains weather on a scale no atmosphere could hold. Hot gas rises from the Milky Way, cooler material returns, and enormous lobes of energetic particles stand on either side of the galactic center. Stars help drive the circulation. Massive stars pour out winds during their lives. When some end as supernovas, expanding shock waves heat and stir the surrounding gas. Many events together can open channels away from the crowded disk. The heated gas may reach millions of degrees. At such temperatures, atoms lose electrons and glow mainly in ultraviolet and X-ray wavelengths. Human eyes would find the region dark, while space telescopes record a broad luminous haze. Buoyant, overpressured material rises several thousand light-years. It carries elements made inside stars, including oxygen and iron. The flow is not a narrow jet from one chimney. It is a changing network of bubbles, loops, and diffuse layers. As the gas expands, it cools. Some condenses into clouds and falls back toward the disk. Astronomers call this circulation a galactic fountain. The name gives a graceful shape to a process lasting tens or hundreds of millions of years. Returning material can mix with fresher gas arriving from outside the galaxy. Together, they replenish the disk, where dense clouds may eventually form new stars. Matter expelled by one generation can enter the raw material of another. Clouds moving at unusual speeds provide clues. Some high-velocity clouds sit above or below the Milky Way and travel differently from ordinary disk rotation. Measurements of their distances, composition, and motion distinguish falling material from tidal debris or external gas. Background objects help set those distances. Light from a remote star or quasar passes through a cloud. The cloud absorbs selected wavelengths, leaving dark lines in the spectrum. If a nearer star shows no absorption while a farther one does, the cloud lies between them. This method turns distant lights into depth markers. The cloud itself may be too diffuse for a sharp edge. Its atoms still sign their presence in the colors they remove. Above the galactic center, the scale grows larger again. The Fermi Gamma-ray Space Telescope revealed two vast lobes extending north and south of the Milky Way's plane. Together, the structures reach about 50,000 light-years from end to end. They are called the Fermi bubbles. Gamma rays do not have visible color, so published images translate their energy into colored maps. The paired shapes appear crisp against a more complicated sky. Recognized in 2010, the bubbles emerged through careful subtraction of foreground emission. Their edges and broad symmetry point toward a powerful event or sustained activity near the galactic center. The exact history remains unsettled. One family of explanations involves a past feeding episode from the central black hole. Another emphasizes intense star formation and many supernovas near the center. Both can send energy and particles far above and below the disk. The event was enormous, but it was not recent in a human sense. Models commonly place important activity millions of years in the past. The structures now persist as evidence spread across a large fraction of the inner galaxy. Microwave and X-ray observations reveal related features. Comparing wavelengths helps separate magnetic fields, hot gas, and high-energy particles. No single band carries the full account. The north and south lobes are not perfectly simple twins. Foreground gas, viewing geometry, and real differences affect their appearance. Researchers continue measuring their spectra, edges, and possible motion to test competing origins. From the solar system, the bubbles loom across wide regions of sky. The viewpoint lies inside the galactic disk, far from the center. Their hourglass geometry must be reconstructed from projected light, much as the solar system's planes are inferred from within. Here, above and below, no longer refers to sparse leftovers around one star. It describes a route taken by gas and energy through the Milky Way. Disks create poles, and poles become channels where material can move away from crowded middles. The same broad principle appears without making the systems identical. A protoplanetary cloud flattened through collisions. Galactic disks form through gravity, rotation, cooling gas, and long merger histories. Each leaves more open directions perpendicular to its average plane. Open directions invite circulation. Solar wind passes over the sun's poles. Comets occupy a distant sphere. Galactic gas rises from supernovas, cools, and returns. The universe does not reserve its upper rooms for emptiness. Even the largest structures remain gentle from here. Gamma rays arrive as occasional counts in a detector. A high-velocity cloud leaves a thin absorption line. Stellar streams shift by a fraction across the sky. Evidence is often quiet. It accumulates in catalogs, mosaics, and years of repeated measurement. The grand scale enters human rooms as small changes in current, color, and timing. That is how the upward direction has been explored so far. Not by a ship sailing straight above everything, but through a handful of tilted paths and many carefully chosen lines of sight. The ecliptic began as an invisible floor beneath the planets. From its edge, the solar system looked thin. Above it, Voyager turned home from a high balcony and found Earth in less than 1 pixel. Farther inward, Ulysses spun through the solar wind with no camera. Its instruments counted fast particles over the poles. Decades later, Solar Orbiter lifted slightly beyond the old viewpoint and saw the sun's southern cap as a textured field. Beyond the planets, a neutral atom crossed the unseen boundary of the heliosphere and traveled back toward a detector. Somewhere much farther out, a frozen body continued an orbit that may take millions of years. 2 celestial roads crossed the night at a steep angle. One belonged to the planets, the other belonged to the Milky Way. Away from both bright lanes, telescopes gathered ancient galaxies through cleaner windows. The view then widened beyond any mission. Old stars wandered through the galactic halo. Gas rose above the disk, carrying the ashes of stars. 2 immense gamma-ray lobes kept the outline of activity long past. All of those directions are present, while an ordinary room remains still. The building rests on a turning Earth. Earth follows its near-flat lane. The sun moves through a tilted galaxy, and the galaxy carries its faint halo into a deeper dark. No universal arrow hangs over the scene. Local floors are enough. A planet supplies one. An orbit supplies another. Each frame holds for a while, giving names to motion before the names soften again. The machines that found these patterns were small. Their antennas, shields, cameras, and particle counters were made by hands that could never travel beside them. Still, a signal returned. A dot appeared. An unseen wind acquired speed and direction. There is tenderness in that scale. A species held close to one planetary plane learned to measure the regions it could barely visit. It did so without filling them, and without needing to stand above the whole arrangement at once. The room may keep the smallest frame now. Its walls are near. The air is familiar. Beyond them, the planets continue around the sun without sound, each following the old disk that shaped it. The pale pixel can fade. Meanwhile, the spinning probe can coast beyond its last command. Solar wind may pass through darkness without needing to be followed. The distant comet has time for its long turn. Meanwhile, the galaxy has time for gas to rise and settle. Nothing in those motions asks to be completed tonight. Gratitude can remain for the instruments that looked, the people who checked, and the quiet universe that offered evidence. Then, even gratitude can loosen its hold. The useful floors are still beneath the world. Those greater directions can return to their patient distances. Rest may take the place that explanation occupied. Good night.